Okay, we had just talked about penalty methods, and while we saw that those were relatively straightforward, both to implement and to understand, they're not particularly great algorithms. So we're going to talk about the first of our state-of-the-art methods, things that are currently in use. This one is called sequential quadratic programming. But before we do that, we're going to motivate with a few simple problems along the way. So one of the ideas, and this is kind of roughly speaking, but this is something we're going to leverage, is that we know how to solve unconstrained problems. So we're going to try to take our equality constrained problems and convert them to unconstrained. That's kind of similar to what we did with the Lagrangian. Both of these ideas are actually, right? And then we would take our inequality and convert them to equality constrained, because then we could, continue that chain. This is essentially what we did when we formed the KKT conditions. Remember that we, in this step, we formed a Lagrangian, which made an unconstrained problem, and we added slack variables, and that made it equality constrained. So we're going to use basically the same idea here, essentially try to solve the KKT conditions, but in an algorithmic approach. So as a warm-up, let's do a simple problem. If you were in class, we did this exercise. If not, I encourage you to pause and try it on your own. But we're just going to do a simple 2D variable or two variable problem with just one constraint and just an equality constraint, just to try and get some ideas here. So we're going to minimize x squared minus 8x plus y squared minus 12y plus 48, subject to x plus y equals 8. All right, now, first thing to note is that this case is simple. We could have, for example, we could solve like y equals 8 minus x, plug that in here, take derivatives with respect to x, be a simple problem. But we won't use that approach because in general, we can't do that, right? If this was, say, the sine of x plus the cosine of y, I couldn't explicitly solve and plug things in. Or if I had many constraints, right, that would also make things more difficult. So we're not going to use that approach. Instead, we're going to try to use the Lagrangian. And like I said, if you haven't tried this, I'd encourage you to pause and try that now before we work it out. Another thing to note is that this constant, right, is actually just irrelevant, right? Anytime I want to minimize or maximize some function, adding to a constant to it doesn't change the solution. Of course, it changes this number, the objective number, but the actual optimal solution, right, the optimal x, y values here won't change. It would be like saying I want to minimize the drag of this vehicle, or I want to minimize this drag of this vehicle plus 2 pounds, right? It doesn't actually change the solution, it just scales this number. So without losing anything, we could just get rid of that, just to simplify. All right, so the hint I gave is what we saw in the optimality conditions. Let's form a Lagrangian. Let's form this as an unconstrained problem. So the Lagrangian is now a function of x, y, and lambda. Remember, it's going to be f of x. Well, actually, let me just write it generally again so we can recall. Lagrangian, and we'll write it as a generic x as a vector. In this case, our x would be x and y as a vector, plus the sum of lambda times all of our inequality constraints. Okay, so in our case, there's just one constraint. So it's going to be x squared minus 8x plus y squared minus 12y. That's my objective here. And then I add lambda times this. I need to write it in the form h equals 0. So I'll just move the 8 over. So I have plus lambda times x plus y minus 8. Okay, so now I have a Lagrangian. It's a function of 3 variables, x, y, and lambda. And so we do what we've normally done in, say, calculus to find a minimum or extremum. We take derivatives and we set them equal to 0. In this case, we have 3 derivatives, partial derivatives, x, y, and lambda. So that will give us 3 equations, 3 unknowns. So we'll take the partial of L with respect to x. It's going to give me 2x minus 8 plus lambda, and I set that equal to 0. I take the partial with respect to y, and that gives me 2y minus 12 plus lambda equals 0. And I take the partial with respect to lambda, and that gives me x plus y minus 8 equals 0. Okay, and it's not a coincidence that we just get back our constraints. This is our constraint as one of the equations. It shouldn't be surprising that the solution to this problem better satisfy the constraints, right? And this will be true every time because as I add more constraints, I add more lambdas. And so I take the partial with respect to each lambda, that's a new variable. And so I'll just get each of these h's out, h equals 0 or hi, each one, right? So what I've done here is I'm going to have three equations, three unknowns. In general, they could be complicated nonlinear equations. In this case, I chose them, so they're really simple. They're just linear. But in general, they could be some nonlinear function. And so how would I solve that? Well, there are many solution approaches, but just generically, a simple method would be Newton's method. We'd have to iteratively solve for um, these systems of equations. But in our case, they happen to be linear, or they are linear by design here. So we can solve them pretty straightforwardly, just as a linear system. I could write that like this, x, y, lambda. Okay, so that first equation, I have 2x plus 0y plus 1 lambda equals 8. The second equation here tells me that 0x plus 2y plus 1 lambda equals 12. And then finally, the last equation says 1x plus 1y plus 0 lambda equals 8. Right, so I could solve that, and I get x equals 3, y equals 5, lambda equals 2. Okay, so that is the optimal solution to my original problem. Okay, so there are a few takeaways from this example here. One is that this is an approach we could use quite generally. We could have many constraints. We just form the Lagrangian, take partial derivatives. And what we're going to get is a system of equations that are going to be nonlinear. And so, like I said, we could use Newton's method or some other approach, but some iterative approach in general to solve that system of equations. Another thing we notice is that in some cases, we might get a linear system, in which case it's really easy. So the question is, what were the conditions that made this linear, or more generally speaking, what conditions would make this linear? So think about that for a sec. One that's maybe more obvious is that I'm going to get all of my constraints back, right? Every constraint is going to be another equation. And so if I want linear equations, then every one of my constraints has to be linear. And that's the case here, right? This is just a linear function. The other condition here is that I'm going to have derivatives of my objective. And if I want the derivative of my objective to turn out to be linear, then my objective has to be quadratic, right? Because the derivative of a quadratic function will be linear. So if I have a quadratic objective and linear constraints, then my KKT conditions are just going to be a bunch of linear equations. And this is what we call a QP, Quadratic Programming problem. We might call it a quadratic optimization problem today, but programming is a word that's been historically used and is kind of stuck, especially this acronym QP. So we'll still refer to that at times. Okay, so let's kind of see that more rigorously. We kind of said some general principles from here, but let's see how that might work. So let's say I've got some general function. I'm going to write a little bit over here to give myself room. I need to minimize f subject to h equals 0, and there are many h's potentially. Okay, so I can form the Lagrangian. It's going to be f of x plus the sum of the lambdas times h, or I could write that as a transpose. I'll write it this way, h transpose times lambda, or I could write it the other way, it's just a dot product. Okay, and now I'm going to take partial derivatives and set them equal to 0. So the partial with respect to x and the partial with respect to lambda. The partial with respect to x just gives me the gradient of f plus the gradient of h. This is now a matrix transposed times lambda. I want that to equal to 0. And then the partial of this equation with respect to lambda is just h, right? And so I get h equals 0. Okay, that's a vector equation. This is what we've already seen. Those are our KKT conditions for equality constraints. But what we're going to look at now is an algorithmic approach, as we could say, well, this is just a bunch of equations in general, not linear. This is a bunch of equations. So we could solve this with Newton's method. Recall what Newton's method is that for ND, we've seen this a few times, but let's say I wanted to solve R of U equals 0, right? This is a vector, and this is a set of equations. I guess I should, since we've been using vectors lowercase, I should write it that way. Okay, then Newton's equation tells me that I could take this as my iteration. I take the gradient of R, and this is going to be a matrix now, so I'll just make sure that's clear. I multiply that by some step size in U, so that would be the delta S, if you will, or delta U, sorry. And then equate that to minus R. Okay, so that's just an iterative process here. In our case, U, I'm gonna give myself some room here. U, sorry, just gonna make sure how much I gotta fit. U here is that it's just those variables together, both X and lambda, right? Those are both unknown. So you could think of it as just one big set of unknowns, which we'll just call it U. So if we take the derivatives, so if we take what we've got here, this equation here, these are my residuals, R, and I'm just gonna use this formula here. So that's gonna look something like this. I'm gonna have a matrix, and then I'm gonna have these steps. I'm gonna have a step for X, a step for lambda, and that's gonna be equal to minus R. So that would be minus H here, and this one here, this is the gradient of my Lagrangian. So this is minus grad L. Okay, so I just filled out this side, the minus R side. Here I have to take the derivatives of R. So this is gonna have 4 entries. This is gonna be the partial of these residuals with respect to X, and the partial of these with respect to lambda, and the partials of these with respect to X, and the partials with respect to lambda. So the partial of this first equation with respect to X, that's just gonna be the second derivatives with respect to X of the Lagrangian. This function, now the derivative with respect to lambda is just this, this term there, gradient of H transpose. And then the derivative of this one with respect to X, that's just gonna be the gradient of H. And then the gradient of this with respect to lambda, that's this corner here, that's just 0, doesn't have any dependence on lambda. Okay, so that tells me what to do at each iteration. So let's just step back and see what we're doing here. I've got some general complicated equations. These are my KKT conditions. I can't necessarily solve them directly like I could in a linear case, so I'm going to use Newton's method. And this is a step in Newton's method. And so these are my step sizes. So that means my next iteration, after I solve this system of equations, it's going to be Sx. I just update my X values and I update my Lagrange multipliers. That's a S lambda, sorry. And then I do it again. So I calculate these steps from solving this system of equations. This is now just a linear system of equations. I solve it, I get a new iteration. So now I have to go back and compute my gradients and my Hessians, populate this matrices again, this vector, solve, and I just keep iterating until I satisfy my convergence criteria and I've solved these KKT conditions. This is more or less what we did, except for we didn't have to iterate because this step here just gave me linear equations. All right, so this is one way to think of how sequential quadratic programming works. It's just applying Newton's method to the KKT conditions, right? So again, the KKT conditions are just a bunch of equations that we set equal to 0. And we just use Newton's method and iteratively solve that set of equations directly. Well, let's think about another approach, or another way to think about it. It's actually the same approach, but it's a different way to think about it. Remember that we saw that if we had a QP, a quadratic programming problem, then things turned out to be pretty simple. So another idea is that we could take our general function, this one here, it's pretty complicated, but locally we could approximate it as a QP, right? We could always just take a Taylor series, for example. So let's look at that. Here's, for example, a QP. This is a quadratic objective, and this one just has one linear constraint, but in general, it might have many. So let's say I have an equality constrained, because we're only dealing with equality constraints right now, right? Quality constrained QP. Well, this I can write generally as like this. I could say 1/2 X transpose QX plus F transpose X. That's a quadratic objective, so I'm now writing it in a matrix vector notation. This 1/2 is just convention. It doesn't mean anything. It just means I've got quadratic terms here in X. I've got a linear term here in X. I could have a constant, but as we discussed, that doesn't change anything. And then I have a linear constraint, and these are only equality constraints. So this is a matrix vector, so this is many constraints potentially, okay? This is very general. This covers every equality constraint QP you could think of. I just changed the numbers in Q, F, A, and B, but any possible equation where I've got a quadratic objective and linear constraints in any dimension, I can write it in this form. All right, so, and if this was like, say, I was approximating my optimization function, I did a Taylor series, this would be my Hessian, for example. This would be the gradient of my objective, potentially. And these would be just a linear, this would be the gradient of my constraints and just the constraint value. So we could do a linear approximation of the objective, or sorry, quadratic approximation of objective and a linear approximation of constraints, for example. But we saw in our simple example that if I have a QP, an equality constraint QP to be specific, then the solution is really simple. And we can see this generally here. This is the same thing we did before, but now in a general way. I'm going to create the Lagrangian. It's going to be F plus, lambda transpose times H. So in this case, that's 1/2 X transpose QX plus F transpose X. That's F plus lambda transpose, and I need to write in the form H equals 0, right? So I'll do AX minus B, for example. Actually, to be consistent with the book, let me just change my linear constraint to be this. I had used a positive sign, so just so not to create any confusion. It doesn't matter, you just have to be consistent on the signs. So now we take the partial derivatives, partial with respect to X and the partial with respect to lambda. We set those equal to 0, just like we did before. So if I take the derivatives out with respect to X, this gives me QX, and that's why we put the 1/2. It kind of cancels that quadratic term out, just as a convenience, plus F plus A transpose lambda. Okay, and I set that equal to 0. And then if I take the derivative with respect to lambda, just like before, we just get the constraints. AX plus B equals 0. So I could write that as in a block matrix form. X lambda, sorry, X's and lambda sometimes look a little too close to each other, at least in my handwriting. So this first equation here, let's write that down. That's Q times X plus A transpose times lambda equals minus F. And then the bottom equation says A times X plus 0 times lambda equals minus B. Okay, so what we've shown is that if I have a QP, equality constrained QP, I'm going to get a linear system of equations, which is great. In fact, this is exactly, like I said, this is exactly what we did here. This was a QP, had a quadratic objective, had a linear equality constraint. We formed Lagrangian, we took partial derivatives, it was a linear system of equations. All we've shown now is that that is always the case if you have an equality constrained QP. And this is great because this is super easy to solve, right? It's just a linear system of equations. We're good at solving those. In fact, this is so helpful that it's used in a lot of applications. So for example, you may have done least squares fitting before, like you had a function and you wanted to fit say you wanted to fit a quadratic to it, or you want to fit this curve or whatever. The coefficients were linear on that function. And so you use what's called a least squares. What that is actually one of these things where we're, say, minimizing sum of squared errors, so we get a quadratic objective. Another example is if you're doing controls, you may have heard of an LQR controller, the linear quadratic regulator. The idea there is that your dynamics, you approximate the dynamics as linear, right? We often do that anyway in dynamics. But then you form a quadratic objective. So you would say have some quadratic sum of errors or plus maybe some sum of control efforts or whatever. But we intentionally approximate our objective as quadratic, and we do that because we can solve this very efficiently. And this is going to be, as long as Q is positive definite, it'll be convex, meaning it has one solution, and we'll find that global optimum really quickly and efficiently. And so that can be very advantageous for controls applications where we need to, solve an optimization problem again and again and again repeatedly as we get new information. But it's also going to be useful here in this optimization context. So the idea was that I've got some general function like this, f and h. I don't know anything about them other than what I get locally. But locally, I can compute a Hessian, I can compute a gradient, I compute gradients, a Jacobian of my constraints. So I can approximate my function locally as a quadratic objective and a linear constraint. And if I do that, I can very quickly solve that optimization problem, take a new step, and then update my Hessian, my gradient, my Jacobian, all that, and do another step and so on. So just to show that maybe a little more clearly how that's actually done, actually, it's not clear necessarily what objective we should use, but here's what's done, and this is maybe somewhat in retrospect, is that we minimize an approximation, a second order approximation of the Lagrangian. So we take the second derivative of the Lagrangian rather than just the objective directly. We take the Lagrangian. So this is the gradient of the Lagrangian. So this is my quadratic approximation of the Lagrangian. The real Lagrangian is something nonlinear. I don't know what it is necessarily, but I'm just doing the second order Taylor series. And again, the constant term doesn't contribute. So, this is formed by the gradients of my objective and constraint and the second derivatives of my objective and constraint. And I need a linear constraint. So I'm going to take an approximation. Again, the first order Taylor series of my constraint. This is a matrix, this is my Jacobian matrix. Gradient, and these are, my constraints are h equals 0, right? Plus h equals 0. So this is h in general is some nonlinear thing, but this is a linear approximation of some arbitrarily complex function. So it turns out that if we make this choice that we're going to approximate our constraints as linear, and we're going to approximate our Lagrangian as quadratic, then we can do this, right? We can solve this equation. It's going to be a linear, this is a QP, so we can solve it. It's going to be this linear set of equations. We take a new step for x and lambda, and then we do it again. We solve this new QP. So what we're doing is we are sequentially solving quadratic programming problems. Hence the name of this method, Sequential Quadratic Programming, or SQP. So it turns out that this choice here, if we do a little math, we're going to reduce it to this form here. What it's going to look like is this. I kind of got it drawn there in the corner. Second derivative Lagrangian, gradient of h transpose. This is a matrix, right? This is the matrix, gradient of h. 0, step of x, step for lambda. And it actually doesn't come out in this form immediately. You have to do a little bit of math, but this is what it's going to look like. Okay, this is a linear system of equations. This is that form right here. Right? This is what this looks like. If we go back to this equation, this is when we just took Newton's method directly. Notice this is exactly the same. So it's the same method either way, it's just two different ways to interpret what we're doing, right? And so then the last step here is after you solve that, just like before, we update x. And potentially, we could do a line search in here rather than accepting that step directly. We could, just like we did before, do a line search. But that's the idea. Okay, so again, two interpretations here for an SQP. One is for an equality constraint SQP, is that we are going to take our KKT conditions, or just a set of nonlinear equations, and just apply Newton's method to it. And that's going to be an iterative method. And we'll just use Newton's method, solve those equations. Another approach is we could say, well, let's take my gradient and Hessian and all that, and locally I can take a quadratic approximation of my Lagrangian and a linear approximation of my constraints. That forms a QP. QPs are easy to solve, just ends up being a linear system. And so I solve that, take a step, and then I do it again. I sequentially solve QPs, or quadratic programming problems. So either way, the method is exactly the same. The numerics are the same, right? This equation is exactly the same. It's just two different ways to think about what we're doing, and depending on and both can be useful to think about. Kind of motivate different approaches. Even though maybe the Newton method seemed maybe more natural, perhaps this idea of sequentially solving QPs will be maybe a more useful idea as we move to inequality constraints. But we're going to stop here for today and handle the inequality constraints next time.